screen sharing, please?
Yes, sir, ma'am. I'm just asking to student.
Yeah, thank you.
Uh, Hello, ma'am.
Yeah.
Am I audible?
Yeah.
Yeah. Okay. So now
Okay,
team
now it
has.
is fine. Yeah,
Yes, ma'am.
I
Yeah.
can.
Okay, ma'am. One important instruction, ma'am, for
Yeah.
everyone. Actually, so hello everyone. Good evening. So, ma'am, will revise the concepts of from week 9 to 12, which cover random variable and distributions and all. Okay, so please do not ask any general doubts. The rest of the general doubts we will be covering our sessions. Okay. Yes, ma'am. I think we can start, ma'am.
Am I audible?
Yes, ma'am. Yes.
Okay, and good evening, everybody. 1 second, I think I have. Okay, I think we'll wait for another minute.
Good evening, ma'am.
Good evening, everyone.
Good evening, ma'am.
Yeah, good evening. Okay, Prashant, can I start?
Yes, ma'am. We can start.
Prashant?
Yes, ma'am. Yes, ma'am. We can
Yeah.
start now. Yeah.
Okay, right. Okay, because there are only about 31 participants, but so good evening, everyone. I think in the interest of time, we'll start and people can join us and when they are ready. The intent of today's session is to just revise the concepts of random variables and distributions. So the agenda is to give you a review of random variables. What is a probability mass function? What is a cumulative distribution function? The notion of expectation and variance. Then talk about a few discrete distributions and talk about a few continuous distribution. Since we have 2 hours, the way I have planned it is I will talk for about 30 minutes on each one of them. And at the end of, so I'll do 30, 30, 30, and then afterwards we'll have 10, 10, 10 minutes for doubts and clarifications, if any, on each of the modules. I hope that is okay. Yeah? Is that
Yes,
okay with
ma'am.
all of you?
Yes,
Right,
ma'am.
so that people can just clarify it as a so that there is a flow. So first I have modularized it into, first thing is I will talk about review of random variable, and then a notion of random variables, then we'll come to notion of discrete distributions, and then we will look at some continuous distributions. Okay, so to start with, I'm going to start with what is the notion of a random variable. And are you all able to see my screen now? The 1 second, I think I need to share the screen. Yeah. Are you all able to see my blank screen now?
Yes, ma'am.
Yes.
Yes,
Yeah,
ma'am.
it's a OneNote screen. I hope it's visible, right?
Yes, ma'am.
Right. So I'm going to introduce what is the notion of a random variable. Please permit me to switch off my video to just save some bandwidth. Okay. As long as I'm audible, I think that is good enough. So what is the notion of a random variable is, we know that when we have a random experiment, okay, the outcomes of the random experiment give me what is called a sample space. Agreed? The outcome of a random experiment, all the outcomes give me what is called a sample space. For example, if I do twice, toss a coin twice, I get HH, HT, TH, and TT. Okay, this could be anything with two outcomes. I'm just going to write it this way. If I roll a die once, it's just going to be 1, 2, 3, 4, 5, 6. This is going to be the outcomes. So the outcome of any random experiment is what I call the sample space. Now, the idea is these are outcomes. Sometimes I might not want outcomes as such, but I would want to map each outcome to what I call a real number. I repeat, sometimes my interest might not be in what is the outcome. Okay, we are not interested in the result, but we might be interested in some numerical value that is determined by the result. So in this case, suppose the value I'm determined is, I am looking at number of heads. This is what I am interested in knowing. Okay, number of heads. How many heads are associated with this outcome?
2,
2.
2,
With this outcome?
1,
1. With this outcome?
1,
1. With this outcome?
0.
I could also talk about number of tails, and it is going to be the same thing, right? Okay. So then afterwards, I could also toss a coin. I could also look at number of tosses before the first head. Number of tosses before first head. Okay. In this case, how many tosses do I have before first head? In the first thing? How many tosses do I have before the first head? When which toss, or the toss of the first head? Toss in which first head appears for the first time? Appears for the first time. In this one, which toss does head appear for the first time? In this,
HH and HT.
it is the first toss. In this, again, it's the first toss. Here head appears for the first time in the second toss. Here head does not appear at all. Is that clear? So in the same sample space itself, I can define different random variables. Is this clear, the concept?
Yes, ma'am.
Yeah. So what we discussed again, when we go back and discuss, is my PDF visible now?
Yes, ma'am. No, ma'am.
Now?
No, ma'am.
No, ma'am.
Not yet. Okay. One second. Is the PDF visible now?
No, yes, ma'am.
Yes, ma'am.
Yeah, right. So if you look at this rolling as a dice twice and the sample space, I have 36 outcomes in my experiment. And here I've defined two random variables. One is I'm looking at the sum of the outcomes. That is one random variable. Okay. Now, if I define X to be the sum of the outcomes, X is the sum of outcomes. What are the values this X can take? If X is the sum of outcomes, what are the values this X can take?
2 to 12.
It can take 2, 3, 4 up to 12. Agreed? Now, the next I'm going to talk Y is the greater of the two outcomes. I can define this like that, and if it is a tie, it would be the same number. What are the values Y would take?
1 to 6.
It will take the value 1, 2, 3, 4, 5, 6. Right? Again, it's the same thing. Now I can define another variable Z to be the difference of outcomes. What would be the value this would take? Difference in outcomes. I can define it, right? So what is the value this outcome would take? 1 minus 1. That is a 0.
0, 1,
1
2,
minus
3.
2 is a minus 1. Okay, so what would be the maximum value is? It goes from minus 5, minus 4. That is how it would take, right? Agreed? This would take
Yes,
a
ma'am.
minus 5. This would take a plus 5. So I'll get a minus 5 to plus 5. Would you all agree? Now I can also define this to be absolute difference of outcomes. And what are the values that would take? Absolute difference of outcomes?
0 to 5.
0 to 0, 1, 2, 3, 4, 5. So the idea is I'm not interested in the outcome itself, but I'm interested in some function of the outcome, which is a numerical quantity. Is this clear? That is what I call a random variable. Is this clear?
Yes, ma'am.
Right? So now when I talk about a random variable, here I have defined two random variables on the screen. One is the sum of outcomes and y is the lesser of two outcomes. The next important thing that we want to know is what is the distribution of a random variable, because a random variable is taking values. It is not the same. So we are interested in knowing whether there is a distribution. If yes, what is that distribution? Okay, now what is the chance with which x takes the value 2? How many times is x taking the value 2 here? If I have to count, it is taking it here. Any other place? X is taking the value 2. What is the chance with which x takes the value 2? So I'm looking at the
1.
distribution of 36 outcomes. How many outcomes does x take the value 2?
1.
Only 1. 3. This and this, right?
Ma'am.
Yeah. Hello?
Yes,
2,
ma'am.
ma'am.
2, right? Similarly, what is the chance with which y takes the value 1? You can see it is all these values. It is this, it is this, it is this. Okay, you can see that y takes the value 1 with these are the value number of times y takes the value 1. So I have a distribution of x, I have a distribution of y. So the distribution of x is probability of x given to equal to 2 is 1 by 36, 2 by 36 up to x equal to 12. This is the probability distribution of x equal to I, and this is the probability distribution of y equal to j or y equal to I. So in other words, corresponding to any random value, I have what is called the distribution of a random variable. Now, before we go and look at what is the probability mass function, let's distinguish between what is a discrete random variable and a continuous random variable. A discrete random variable takes at most a countable number of positive values. So what does it take? X takes the value x1, x2, okay, and it could be xn if it is finite, or it would be x1, x2, so forth. Let me give you an example. Like I am tossing a coin. Okay, I'm tossing. Let the experiment be. Are you able to see my OneNote here? The blank
Yes,
page,
ma'am.
right? So I'm going to describe a experiment, okay, which is tossing a coin till I get a head. Till I get a head. What is the sample space of this? I keep tossing a coin till I get a head. What are the possible outcomes?
Head or tail.
Head or tail, that's it. Tossing a coin till I
From
get a
1
head.
to 3 up to infinity.
I could get a head in the first toss. I could get a head in the second toss. I could get a head in the third toss. These are my outcomes. Would you agree? I'm tossing a coin till I get a head.
Okay.
Right. So what are the possible outcomes? I could either get a head in the first toss, or I could get a head in the second toss, or the third, so forth. Is this clear? Now
Yes.
let me define a random variable x to be the number of the toss in which I get a head. So what is the value of x I get here? With
From
the
1
first
to
outcome.
3.
This
It's
is
1
1.
or infinity.
This is 2. This is 3. This is 4. So the value x takes is discrete, but it is countably many, but it is infinite. Is that clear? Whereas in the earlier example where I just had head, 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 tail, tail, head, and tail, tail, and I was counting the number of heads, this was 2, 1, 1, 0. This was again countable, but it was finite. So is this clear as to what this statement says? Is the PDF visible? That a random variable can take on a finite number or countably infinite number of different values. Is the PDF visible?
Yes,
Yes, ma'am.
Yeah. So this is when the random variable. So the random variable that I had defined, okay, in one I had finite number, that was x was taking value 0, 1, 2. In the other I had x taking value 1, 2, 3 up to infinity, but both of them it was countably infinite. So in this case my x was a discrete random variable. On the other hand, if I'm looking at the time taken for a person, so suppose I define a random variable or a experiment to be the time taken for a or the lifetime of a bulb, what would be the sample space of that? Lifetime of a bulb. How would I describe the sample space of that?
Maybe we can put it in number of days or hours starting
Number
with
of
1.
hours. Suppose I'm talking about hours. So that could be 0 is less
0.
than t is less than infinity. Okay, it's a continuous time. Okay, and if I'm looking at the sample space that it is at least a bulb which has lasted for 10 hours. Okay, and that way then I know that 10 is greater or equal to 10 is less than, and within 50 hours I'm giving you a interval where it is lasting. So here in this case the random variable takes what I say a continuous random number value in an interval. So is the basic difference between discrete and continuous clear?
Yes, ma'am.
Yeah.
Yes, ma'am.
Right.
Yes,
So
ma'am.
now once I have a discrete random variable, remember that whenever I talk about a discrete random variable, just as when we had types of variables, we had broadly defined them to, especially numerical variables, we had broadly defined them to be discrete and continuous. And at that point also we said discrete is something where you are involves counting, whereas continuous is something that involves measuring. So whenever you are counting number of something, number of hits, number of people, then you are modeling it as a discrete random variable. On the other hand, if you are measuring, okay, amount that is you're measuring, which could be time, which could be height, which could be weight, where you measure, that's where speed, you measure speed, you don't count speed. You measure the temperature, you don't count temperature. You measure the height, you don't count the height. This is where you'll model all these variables as a discontinuous random variable. Okay, so the first thing is, given the nature of the variable, we need to decide whether we are modeling it as a discrete random variable or a continuous random variable. So far so good. Is this clear? Yeah.
Yes.
Okay.
Yes, ma'am.
So
Yes,
now
ma'am.
next is the concept of what we refer to as a probability mass function. Is my one note clear, visible now?
Yes,
ma'am.
yes, ma'am.
Yeah, right. So what is a probability mass function? Again, let's go to this random variable. I can define x takes the value 0, 1 and 2. Okay. Here I can define x which takes the value 0, 1 and 2. What is the probability with which x takes the value x? That is takes the value 0.
1.
Probability with which x takes the value 0.
1 by 3.
1 by 4. That
3.
corresponds to this outcome. It takes 1 by 4. X takes the value 1, corresponds to these two outcomes. It is either this happens or this happens. Both of them are disjoint. So it is the sum of the probabilities, which is 2 by 4. 1 by 4 plus 1 by 4. Probability with which x equal to 2 is the probability of this outcome happening. which is 1 by 4. This is what we refer to as a probability mass function. So in general, if x takes values x1, x2, so forth, then the probability mass function gives us probability x equal to x1 or p1, probability x equal to x2, p2. The properties are this probability x equal to xi has to be greater than 0 or equal to 0. And since it is a probability which is taking over all these possible values, probability x equal to xi over all xi should equal to 1. So what is 1 by 4 plus 2 by 4 plus 1 by 4? That is equal to
4 by 4.
1.
1.
Okay,
1.
4 by 4, which is 1. So typically you'll find problems. For example, if I had something of this kind, okay, now is this a probability mass function? What is summation probability x equal to xi here? 3 by 4 plus 2 by 4 minus 1 by 4. What is that?
4 by 4. That is 1.
It is 1. But is it a probability mass function?
No, ma'am.
No, no, no.
Because this is negative.
Negative.
Agreed? So I have to have both these conditions satisfied for something to be a probability mass function. Is that clear?
Yes, ma'am.
Yes, ma'am.
Yeah. So I need
Yes, ma'am.
both of them to be satisfied. So let's go back here. This is what we refer to as a probability mass function. 1 by 4, 2 by 4, 1 by 4. Now, given a probability mass function, I can always graph it. So I'll have on my x-axis the value the random variable takes, which is here 0, 1, and 2. And on the y-axis, I'm going to graph the probability of x equal to xi, which is going to be 1 by 4. This would be 2 by 4. And this will be 1 by 4 again. So this is what we refer to as the graph of your distribution. Now, why is the graph of a distribution important to us? The graph of the distribution will tell us about the shape of the distribution. And that shape could be anything, like it could be symmetric or it could be skewed. So you can see that this is the probability mass function. Okay. And given the probability mass function, I have what is the probability, the graph of the probability mass function. Now, what you see on the screens, is the PDF visible? Can you all see a PDF on the screens?
Yes, ma'am. Yes, ma'am.
Yes?
Yes,
So
ma'am.
now
Yes,
you
ma'am.
can see that this is a skewed distribution. It's a positively skewed distribution. Is that clear? Similarly, this probability distribution is a negative skewed distribution. Okay, so you can see this happening. On the other hand, what I plotted here was a symmetric distribution. So is this clear that the graph of the probability mass function will give us what is the shape of the distribution, whether it is symmetric, whether it is positively skewed, or whether it is negatively skewed. So far, so good. Any questions?
No, ma'am.
Okay, right.
No, ma'am.
So the next concept is, once we have told what is a probability distribution, then let's go back here to understand what is a cumulative distribution function. The next concept is that of a cumulative distribution function, also referred to as CDF. The probability mass function is referred to as the PMF. This is the probability mass function. And this is defined for discrete random variables. The equivalent of it in a continuous case is what we call the probability density function. But here we have looked at the probability mass function. Now, what is a cumulative distribution function is? This is all functions. So I have a cumulative distribution function, which is defined for R onto 0, 1. What does it mean is, for any value on the real line, this is my real line, x-axis also on my real line, I'm going to define a function which is probability of this random variable x is less than or equal to a. A is any point on my random variable. Is that clear? And since this f of a is probability x is less than or equal to a, and this is a probability. What would be the range of this function f? Because f of a is probability x is less than or equal to a. What would be the range of f? Because this is a probability
X A comma X.
x, the
0 to
range.
1.
Sorry,
It would
0
be
to
0
1.
to 1. Is
Yes,
that
yes,
clear?
0 to 0 to
Right?
1. It's 0 to 1.
Okay. So now suppose I go back to this example where x was taking value 0, 1, 2. 0 is here, 1 is here, and 2 is here. What is the probability? So when I'm defining a probability mass function, I have defined probability x equal to 0 is 1 by 4. Probability x equal to 1 is 2 by 4. Probability x equal to 2 is 1 by 4 again. Okay. So now here when I define a cumulative distribution function, I am going to need this condition that x1 is less than x2 is less than x3 for all the positive values. Is that clear? So I have 0 is less than 1 is less than 2. Now what is probability x is equal to minus 2? It is not defined. Agreed? So I need to say here probability x equal to I equal to 0 otherwise. Is this clear? I know probability x
Yes.
equal to 0 is 1 by 4. X equal to 1 is 2 by 4. X equal to 2 is 1 by 4. For every other value, it is 0. Agreed?
Yes, ma'am.
Okay. So what would probability x equal to minus 2 be?
0.
0.
0.
What would be probability x equal to minus 3 be?
0.
0.
0. What would be probability x equal to minus 1?
0.
That also 0.
That all of them would be 0, right?
Yes.
Yeah. So what would be the probability x is less than or equal to minus 1? All of them are 0.
All
I'm
of them.
telling this is cumulative. So I'm going to add all those values of the probability till here. So all of them are going to be 0 and I'm going to get only 0. Is this right?
Yes,
Yes,
ma'am.
At x equal to 0, what is the probability x equal to 0? So if I'm asking f of 0, this is probability x is less than or equal to 0. What is that? It is probability x is strictly less than 0. That would be up to 0. And what is probability x equal to 0?
That is 1 by
1
4.
by 4.
1 by 4.
4. So
1 by
at
4.
x equal to 0, it's going to jump to this point. And this point is 1 by 4. Is that clear?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
And this is going to continue. What would probability, what would be f of now? 0.5. This would be probability x is less than or equal to 0.5. Agreed? And
Yes,
what
ma'am.
would that be? That would be just probability x equal to 0 because everything else is going to be 0. So that is going to continue till your 1. It's going to remain 1 by 4. At 1, what would happen? It would become 3 by 4. Agreed? Probability, there is a jump of 2 by 4, right? What is probability x is less than or equal to 1? This will be
3 by
probability
4.
x equal to 1 plus x equal to 0. It's cumulative. You're accumulating it, right? That would be 3 by 4. Agreed? There is
Yes,
a
ma'am.
jump.
Yes,
And then
ma'am.
there's going to remain this at 3 by 4. Right? And what is probability x is less than or equal to 2? It would be 1. Right?
1.
And it would
Yes, ma'am.
continue to be 1. So this is this sort of a graph. You can see there's a jump. It is a discontinuous graph and it is a step graph. So the cumulative distribution function is defined as what is the probability of x is less than or equal to a for every number on the real line. Is this clear? And we have also seen that the distribution function is a step function. Any questions so far?
No, ma'am.
Okay. So now the next concept that we want to learn is that of a expectation of a random variable. So now again, I'm going to go to the condition or the problem that we have seen is x takes the value 0, 1 and 2. And what is the probability mass function? X equal to I. This is 1 by 4. This is 2 by 4. And this is again 1 by 4. This is what we have, right? Now I'm asking, what is the expectation of this x? What does expectation of a random variable give? In a sense, the expectation can be considered as what we refer to as a long run average of the random variable. In other sense, suppose I have a repeated independent observations, okay, then the expectation would tell me what is it is basically what is the weighted average of the possible values of the random variable. Is that clear? It's a long run average. So how is it defined? The expectation of a random variable is defined to be the summation over all xi into probability of x equal to xi over all the values it takes. Is this clear? So what is the expectation of the random variable x here? It would be 0 into 1 by 4 plus 1 into 2 by 4 plus 2 into 1 by 4. And what is this?
This 2 by 4 plus 1 by 2.
1.
It
This
is?
not 1. 4.
Yeah, it is 1,
2.
right?
Yeah, it is 1. Sorry.
Right. Now, how would you interpret what is this 1? For example, let me give you an example of just x taking two values, 0 and 1. Okay, tossing a coin with probability half and half. Probability x equal to 0, I. Okay, what is the expectation of x here?
1 by 2.
It is 1 by 2. Okay, now how would you interpret this expectation of x? It doesn't mean that at some point, see, if I get a tail, I'm saying it is 0. If I get a head, it is going to be. So this, my sample space was just a tail and a head. I associated these are the values. Okay. It doesn't mean that you're going to get something in between tail and a head. What this means is, suppose I continue to keep tossing a coin long enough, then the value, the average value of, I'm going to get a sequence of 0, 1, 1, 0, 0, 1. This is what I'm going to get if I continue to keep tossing a coin long enough. Agreed? Which would be a tail, head, head, tail, tail, head. This is how I'm going to get a sequence. Would you all agree?
Yes, ma'am.
Then the long run average of these values will be half. That's what an expected value means. Is this clear, please?
Yes, ma'am.
Yes, ma'am.
Yeah. So that is what an expected value gives me. And as I said, that the expectation is the analog of a long run average. I would need a notion of variance also. So what is the variance? Tell me. It is a variance of a random variable is a measure of spread or measure of dispersion. Okay. And how do we define that? The variance of a random variable is defined as expectation of x minus mu whole square. And we know in the lectures we have seen that the computational formula is expectation of x minus expectation of x whole square. This is the computational formula. So now let's apply this to the example. I had x taking the value 0, 1, 2. So what are the values x square can take?
0, 1, 4.
1, 4. What is the probability with which x takes the value I? It's going to remain the same, 1 by 4, 2 by 4,
2 by 4.
and 1 by 4. What is expectation of x square? That
3
would be
by 4.
1 into 2 by 4 plus 4 into 1 by 4, which is a 6 by 4.
Yes.
Agreed?
Yes, ma'am.
We already found out expectation of x was 4 by 4. Right?
Yes.
So what would
Yes, ma'am.
variance of x be? Variance of x would be 6 by 4 minus 1 square, which is 6 minus, this is 1, right?
Yes.
2 by 4.
Okay. So this is 2 by
2 by
4,
4.
which is half.
1
So
by
you can compute. So given the discrete random variable, I have defined what is the probability mass function, what is the cumulative distribution function, what is the expectation of a random variable, and what is the variance of a random variable. Any questions so far here?
no one.
Is it all clear, please?
Yes, ma'am.
Yeah.
Ma'am,
This yeah. Yes, please.
ma'am, in the when we compare when we have a lower a decreasing trend, then it is a positively skewed graph, right?
Yeah, this one was a positively skewed.
And if we
Okay.
have an increasing trend, then it's a negatively skewed.
Yes, this is negatively skewed. And this is
All right.
symmetric.
Okay.
This would be symmetric. Okay.
Yes, ma'am.
Is that clear?
Yes, ma'am.
Okay.
Ma'am,
Yeah, please go ahead. Yeah.
ma'am, in the lecture while deriving
Yeah.
expectation for Poisson distribution, you have used the formula expectation of x minus 1.
Yeah, that's what I said.
How variance becomes expectation of x minus
Can you
1?
see my screen here?
Yes, ma'am.
Okay, so variance of x is defined as the expectation of the deviation. Would you till here is it clear?
Yeah.
Variance of x is nothing but expectation of x minus some mu whole square, right? Now I can write this as x square plus mu square minus 2 into x into mu. Mu is a constant now. Would you all agree?
Yes, ma'am.
Right? So I can write this as expectation of x square. Mu expectation of a constant is a constant minus 2 times, this all follows from properties of expectation. I have not gone to that. Minus 2 times mu expectation of x. What is expectation of x? Expectation of x is mu, right? So I can write this as expectation of x square plus mu square minus 2 times mu square, which reduces to expectation of x square minus mu square. So I wrote it as expectation of x square minus expectation of x whole square. This is variance of x. This is a computational formula for variance of x. Is it clear now?
Yes, ma'am.
Yeah. So this is how we can use this, and you can compute the variance of random variables, because this is an easier thing. See, given a random variable x, I can find out what is the PMF of x square. Suppose I give a random variable x takes value x1 0 with 1/3, 1/3, 1/3. What is expectation of x? In this case?
1/3, ma'am.
No, just look at the problem.
It's 0.
0.
It is 0.
Zero.
Minus
It
1
is 0.
into 1/3.
Cancel
Okay.
out.
Right. And the plus 3. Now, what is the values x square would take?
X square
The same
would take
value.
1/9.
1, 0, 1.
We'll just take 0 and 1. What is the probability with which x square equal to 0?
X square
That would be 1 by
1/9.
3.
Oh, sorry.
This would be 2 by 3. So what would be expectation of x square? This would be 2 by 3, right? Agreed. So what is the variance of x square? It would be 2 by 3 minus 0, which is again 2 by 3. Get it?
Yes.
Is that clear?
Yes, yes.
Yes,
Now,
ma'am.
yeah, there is a question. Is it same as expectation of x into x minus 1? No, it is not same as expectation of x into x minus 1. Expectation of x into x minus 1 is expectation of x square minus x, which is just expectation of x square minus expectation of x. Variance of x is expectation of x square minus expectation of x whole square. Is that clear?
Yes, ma'am.
Yeah. Okay, so it's not the same. Okay. Okay.
Yes, ma'am.
I think I have done something. 1 second. Right. It is not the same. Okay. That's why we should be very careful about our, it's expectation of x square minus expectation of x is expectation of x into x minus 1. So it is not the same. Okay. Can we proceed?
Yes,
The
ma'am.
discrete random variable. So now, having established these things, we are going to look at a few discrete random variables. We'll start with what is called the Bernoulli random variable. Okay. Can I proceed? Is there any questions? Can we proceed?
Yes, ma'am.
Okay.
Yes, ma'am. Please.
Right. Now, what is a Bernoulli random variable? Is my notes visible? One note?
Yes, ma'am. Yes, ma'am.
Yeah. So a Bernoulli random variable is a random variable which takes either only two values. Okay. A Bernoulli experiment is an experiment which has two outcomes. And these outcomes are what we typically call as success and failure. Sorry. So these outcomes are what we call success and failure. So when I talk about two outcomes that are success and failure, with success I can give a value. So success and failure. For failure, I can give a value 0. Okay, again, you remember, I'm just going to allocate some value with these outcomes. So anything where I can have two outcomes, I'm going to declare them as s equal to 1 and 4. So what is the probability? And if it is equally like, I assume that the probability of success would be with probability P, and this would be with 1 minus P, because there are only two outcomes. If success happens with probability P, what is the probability with which failure happens?
1 minus
It's going to 1
because
minus
it's total
P.
1.
So a Bernoulli random variable has this as its probability mass function, where it's taking two values, probability x equal to P and 1. So what would be the expectation of this random variable? How would the CDF look? The CDF is also going to look like this. I have two values, 0 and 1. So till it is 0, it's going to take the value 0. Then it would take 1 minus P. It would remain 1 minus P till here. And then it's going to remain P throughout. Is that clear? This would be my CDF.
Yes, ma'am.
Yes, ma'am.
Yeah. So what would be the expectation of this thing? It is just going to be expectation of this random variable is going to be P into 1 plus 0 into 1 minus P, which is going to be just P. Right?
Yes, ma'am.
What are the values x square would take?
Ma'am, 1 and 0.
Again 1 and 0, right?
1 and 0. Yes.
So what is the value of expectation of x square? I know expectation of x is P. That is what I just computed. What would be the expectation of x square?
It's also P. Again
It's
P.
again P.
Again P.
So what would be expectation of x square minus expectation of x whole square? This is
P
going to
into
be
1
P
minus
P
minus
square, which
P
is
square.
P into 1 minus P, which is variance of a Bernoulli random variable. Till here, is it clear?
Yes, ma'am.
Yeah.
Yes, ma'am.
The next thing that we are going to look is what we call a discrete uniform random variable. Okay. Now, what is this type of a variable is? For example, if I toss a die, what are my outcomes? It is 1, 2, 3, 4, 5, 6. If it is a fair die, and I'm going to take x to be the number that I see on the die, the values x is going to take is 1, 2, 3, 4, 5, and 6. What is the probability with which x takes that value? What is the probability with which x takes the value?
1 by
This is
6.
1 by 6,
1 by
1
6.
by 6. 1 by 6, 1 by 6, 1 by 6. I can plot the PDF again, CDF again, which is going to be, I have x is 1, 2, 3, 4, 5, and 6. Till here, it's going to take the value 0. Okay. Till here, it will be 0. Then it's going to be 1 by 6. Then it's going to be 2 by 6. Then it's going to be 3 by 6, 4 by 6, 5 by 6. And then it's going to be 6. Right? This is going to be the CDF. Agreed?
Yes, ma'am.
Yeah, right. Okay. Now, what would be the expectation of this? So this is called a discrete uniform random variable because it is taking the probability that x is taking every value is equal. So if I have n, suppose I have x taking the value 1, 2, up to some n, what is the probability x equal to I? It's going to be 1 by n, 1 by n, so forth, 1 by n. All of them are equally probable. This is called a discrete uniform random variable. What would be the expectation of this random variable? It is going to be 1 into 1 by n plus 2 into 1 by n up to n into 1 by n. Would you agree? Yeah?
Yes, ma'am.
Yes,
So
ma'am.
this I can write, I can take 1 by n common and I can write this as 1 plus 2 plus n. Would you all agree? Now
Yes,
what is this value? You have all learned it. What would this be?
N into n plus 1 by
Sum of the
into n
first
plus
n,
1.
it will be n into
n plus 1 by 2.
n plus 1 by 2. So what would be expectation of x? This is going to be n plus 1 by 2. So what would be the what is n in this case? What is n in this case? It is 6.
It's
So
6.
what is the expectation of the roll of a die thing? X will be
7
n
by
plus
2.
1, 7 by
7
2,
by 2.
which is 3.5. Is that clear?
Yes, ma'am.
Right?
Yes, ma'am.
Okay. Right. Now look at what is expectation of x square. You can find out what is expectation of x square. That would be again 1 into 1 by n plus 4 into 1 by n, so forth. Right? N square into 1 by n. Agreed?
Yes,
Yes,
ma'am.
ma'am. Yes.
Right. So I will not do it, but you can at least find out what it is and you can compute what is your variance of x. Is this clear? Yeah?
Yes, ma'am.
So we have discussed what is a Bernoulli random variable and we have looked at what is a discrete uniform random variable. One of the random variables that arises or appears very commonly is what we call the binomial random variable. Now, when we talk about a binomial distribution, it comes with two very important conditions, that is independent and identically distributed Bernoulli trials. I repeat, a binomial random variable is a set or collection of n independent and identically distributed Bernoulli trials. So if I'm tossing a coin n times and the chance of me getting a head is the same for, suppose I'm tossing a coin once, what is the chance of me getting a head? It is going to be half, right? If I toss a coin 2 times, what would be the chance of me getting a head in each of the tosses? That is going to remain half. Would you agree? The second toss, will the chance of me getting a head in the second toss be different from the chance of me getting a head in the first toss? Hello?
Hello.
Yeah.
Can you repeat, please?
See, I'm tossing a coin once. Right? What are the outcomes?
Head and tail.
What is the chance with which I get a head? Let me assume this is P and
1
this
by
is
2.
1 minus P. Okay. Now I'm tossing it twice. Okay. So what is happening? This could be again a head or a tail or a head or a tail second toss. This is first toss. This is the second toss. What is the chance with which I can get a head in the second toss?
It's 1 by 2.
1 by 2 only, right?
Yes.
Now I toss. So this is the first, second. So I start, I could get a head or a tail. This could be again head or a tail. This is again head or a tail. Third toss is again head or a tail. What is the chance with which I can again get a head in the third toss? Again this is
Same,
this is again going to be 1 by 2, right? Or
Yes.
P, whatever it is. So this so how many trials do I have here? How many times have I tossed the coin?
3 times.
3 times.
3 times. And each one of this is a trial, right? This is a trial. Okay, now again, this would be a HT. This would be again a HT. Each one of them is a independent. So, and each one of them is an identical trial. Can you see this?
Yes, ma'am.
They are identical and they are independent because whether you're going to get a head in this, does it depend on what it was here? On the first toss, whether you got a head or not?
No, it's not dependent.
It is not. Okay. So this is IIT. It is independent and identically distributed. Okay. Now, on the other hand, I give you 4 balls. Okay. Now, let me look. Is my thing visible here?
Yes, ma'am. It's visible.
One note?
Yes,
okay.
ma'am.
Now, in a ball, yeah, please go ahead.
How is it different from the discrete uniform distribution you just taught just now, ma'am?
I'll just tell you one second. Let me do
Okay.
this.
Okay.
Can you see my thing? How many balls do I have in this box?
4.
4.
4.
I'm asking you to take any ball. Okay. So pick up any ball. what are the possible outcomes?
1/4.
Blue.
It could be either an orange ball or a
Yeah.
blue ball,
Blue ball.
right?
Yes.
What is the chance with which it's an orange ball?
Is
1 by
2/4.
1/4.
2/4, 1/2.
One
The
by
blue ball, it is
Same,
1/2. Okay. Now I'm asking you to repeat the experiment. Pick up again an orange ball. Again, what are the possible things?
orange ball. It's now one is picked up, so
Zero,
it will
ma'am.
be 1
No,
by
no,
3.
I'm asking you to replace. Pick up a ball and replace it again.
Okay,
So
okay.
again, you'll continue to have 2 orange and 2 blue balls. In the second trial, what is the chance with which you can get an orange ball?
Again 1/2.
It is again
Again
going
1 by
to be 1/2, 1/2.
1/2,
This is my
yes.
first trial. This is my second trial. Is that right?
Yes.
Okay. Now I'm going to change the advertisement. The trial, this one. I'm going to ask you to pick up a ball. Okay. First trial, I'm going to ask you to pick up a ball. What is the chance with which it's an orange ball? It's going to be 1/2, going to be 1/2, right?
Yes.
Now I'm going to ask you not to replace the ball that you have picked up.
Yes.
Okay, I'm asking you not to replace it. So now what are the possible outcomes in the second trial?
1 by 3 and 1 by 3.
What are the possible outcomes? Not the probability.
Orange
See, the
ball and
first
blue
trial
ball.
could have been
Again
an
orange or
orange
blue.
or a
Orange or
blue,
blue.
right? The
Yes.
second will also be a orange
Orange
or a
or a
blue,
blue.
Or a
Yes.
blue.
right? But the chance with which it's an orange, given the first was an orange, what would
Yes.
that be?
1 by 3.
1 by 3.
What is
1
the
by 3,
chance the
ma'am.
second is an orange given first is an orange? It will be 1/3.
1 by
1 by 3.
What is the chance second is an orange given first was a blue?
First one is blue. That's
2 by
2 by
3.
3.
2
1
by
by half.
2 by 3.
2 by 3.
2 by
Yes.
So
3.
now this is dependent on what was your first choice. Whereas here, the chance that the second was an orange given first was an orange is independent of what was my first choice. Do you understand the difference between independent and dependent here?
Yes,
Yes,
ma'am.
ma'am.
And this here, both the chances are identical. Here it is not identical anymore, right? It depends on what was your first thing. So I am losing this IID condition when I am doing this experiment. Is that clear?
It is clear, ma'am.
Yes, ma'am.
Yeah. So this, if I have NIID trials, Bernoulli trials, I get what is called a binomial distribution. Okay. Now you had asked what is the difference between that and the uniform distribution. Agreed?
Yes,
Right?
ma'am.
That was a question that was asked. Why am I
Yes,
not looking at it as a uniform distribution? Suppose I'm looking at now tossing a coin thrice. Okay. What are the possible values I get? H, 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 T, H, T, H, T, H, H, right? Then I get a T, T, H, T, H, T, H, T, T, and a T, T, T. 8 possible outcomes. Let X
yes, ma'am.
again be the number of heads. So these are the values 1, 0, 1, 2, 3. Agreed. What is the probability with which X equal to 0? This would be 1 by 8. This is going to be 1 by 8. This is 3 by 8. And this is 3 by 8. Agreed. This is a probability mass function.
Yes, ma'am.
Yes, ma'am.
Now, this is not the same, right? In a discrete uniform, the probability X equal to X1, X2, X3, X4 should be 1 by 4, 1 by 4, 1 by 4, 1 by 4. And I'll have a probability mass function which has equal bars. Whereas here, the probability mass function is going to be 1 by 8, 3 by 8, 3 by 8, and 1 by 8. Is the difference clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
This is discrete uniform. This is binomial. Okay. Is the distinction clear?
Yes,
Between
ma'am.
discrete uniform and binomial. Okay. So
Yes,
you can
ma'am,
see
but
that. Yeah.
ma'am, but in the same example you gave,
Yeah.
can you just specify which IIDs are there in this binomial thing, ma'am?
In this
Like,
binomial, I am now having toss 1, toss 2, and toss 3. What is
yes,
my
ma'am.
toss 1? Could be head 1, tail 1. Toss 2 could
Okay.
be head 2, tail 2, 2, tail 2. This could be head 3, tail 3, head 3, tail 3, head 3, tail 3, head
Yes,
3, tail 3. So you can
got
see
it.
that this is 1, 2, and that is how I can get it. Is that clear?
Yes, ma'am. Yes, ma'am.
Right? And
Three
they are
IIDs are there, right?
yeah,
Three
right.
IIDs.
Yeah, so
Yes,
this is all the outcomes are independent of the third toss outcome is independent of what was my toss 2.
second.
Toss 2
Yes,
is independent of what was my toss 1. And they are identical.
yes,
Is that clear?
got it.
Yeah.
Yes, ma'am, got it.
Yeah. So this is how we can have a binomial random variable. So when I look at a binomial random variable, the probability mass function of a binomial random variable is, again, let's look at this. Okay, I have x taking these values, right? How do I, so if I now toss a coin 4 times, okay, what would be the x would take what value? So in general, if x takes the value 0, 1, 2 up to n, okay, I say that if there are only 2 outcomes, okay, any 2 outcomes, the success happens with probability p, failure happens with probability 1 minus p. Then I say that probability x equal to I, okay, is going to give me, so if I say I'm going to have I successes. So I'm going to have something like success, 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 success. This is going to be I times failure, 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 failure. This is going to be n minus I times. Would you agree? Because totally I have n tosses. Is this clear?
Yes, ma'am.
And they are independent of each other. So if I'm going to have independent of each other, probability of success is P, 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 P. What would this give me? This will give me P to the power of I. Agreed?
Yes.
Yes, ma'am.
Because independent product of them, right? Now this is going to be 1 minus P, 1 minus P up to 1 minus P. This would give me 1 minus P to the power of n minus I.
Yes, ma'am.
Right?
Yes, ma'am.
Okay. Now you see that this is one outcome. Now this outcome is same as S F F F F F F into S S S S. This will also give me P to the power of I into 1 minus P to the power of n minus I, right?
Yes, ma'am.
Right?
Yes, ma'am.
So now how many ways can I arrange these I things? That would be n choose I. Would you agree?
Yes, ma'am.
Yes,
So the
ma'am.
probability of x equal to I is going to be n choose I, p to the I into 1 minus p to the n minus I. This is what we refer to as our probability mass function, where I takes the value 0, 1, 2 up to n, and this is 0 otherwise. That is what you see on your screen is the chance, the probability of I successes and n trials is n choose I, p to the I, 1 minus p raised to n minus I. Is this clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So now, as in every case, what is the expectation of the binomial random variable, and what is the before going to the expectation, I'll just tell you the graph. So now typically if let's go back to this graph of a binomial random variable. I know that x takes the value 0, 1, 2 up to n, right? That is what the value it takes. Now let's go back and plot the graph here. For the x takes the value 0, 1, 2, 3 with probability 1 by 8, 3 by 8, 3 by 8 and 1 by 8. I have the graph which is at x equal to 0, it is taking 1 by 8. It is taking 3 by 8, 3 by 8, 1 by 8. Okay. Now I assume my p is half here. Now suppose p is not equal to half, it will not be a symmetric distribution. Okay. So that is what we are demonstrating here. If p is symmetric, okay, this is a graph when p is symmetric. Is this clear? For n equal to 4, and when you look at when n equal to 4 and p equal to 5, p is symmetric. Is this clear? What are the values x will take? X will take the value 0, 1, 2, 3 and 4, which it has taken, and it is symmetric because p is 0.5. If P is not 0.5, okay, if you look at this same n equal to 4 with P equal to 3, it is a right skewed graph. Is this clear?
Yes, ma'am.
If n equal to 4 and P is equal to 0.8, you get a left skewed graph. For the same n, when n equal to 4 and P equal to 0.3, you get a right skewed graph. N equal to 4, P equal to 0.5, you get a symmetric. N equal to 4 and P equal to 0.8, you get a left skewed graph. Is this clear?
Yes.
Yes, ma'am.
Now, if I keep increasing that n, suppose I take n is very large and P is 0.5. So n equal to 40 and P equal to 3, you can see that it is moving here, right? You can see that the shape is something very similar, but it is towards the left. Is that right? Skewed, right skewedness. Now, when n equal to 40 and P equal to n, you can see that it is at the center. Can you see that? Whereas n equal to 40, P equal to 8, you can see that it is shifted to the right and it is left skewed. Is this clear? The shape. This is important when you are looking at a binomial distribution, that for even P need not always be 0.5. If P is less than 0.5, you'll get a right skewed. If P is greater than 0.5, you'll get a left skewed. Is this clear?
Yes, ma'am.
Yes,
Right?
ma'am.
Okay. So now what is the expectation of a binomial random variable? Now, as I said, this expectation, I can represent this binomial random variable and I write that this X is a binomial with parameter. I write that X is a binomial with parameter N and P, okay, where I have N trials. And the probability of success of each of the trials is P.
Please mute your mic, please. Hello.
Hello.
Ma'am, someone's mic is not muted. Noise.
Okay. So I have n trials. I can express this X as X1 plus X2 plus Xn, where each one of these Xi's are an independent Bernoulli distribution. Would you all agree with me? I can express this X because suppose each one of them, what is this? This could be a success or a failure. This could be a success or a failure. This could be success or a failure. And they have the same probability of happening. So to find how many successes in n tosses is counting the number of successes in n independent Bernoulli trials. I can express it as X1 plus X2 plus Xn. Would you all agree with me? Yeah?
Yes, ma'am.
Yes, ma'am.
Now, what is the expectation of each Xi Bernoulli? If Xi is a Bernoulli with parameter P, we saw what was the expectation of that, right? This
Yes,
was
ma'am.
P,
Yes.
right? So what would be expectation of X? This would be expectation of X1 plus X2 up to Xn, which is same as expectation of X1 plus expectation of X2 up to expectation of Xn. Each one of them is P. So P plus P plus P. I'm adding P n times. So what would be the expectation of X? It would be n into P. Is this clear?
It is clear.
Yes,
Right?
yes, ma'am.
Now
Yes, ma'am.
similarly, what is X square? I can express X square as X1 square plus X2 square. Can I do that or can't I do that?
Yes, ma'am. We can do that.
Can I or can't I? Let me look
Yes.
at only two. It is X1 plus X2, right?
Whole
X is
square, I
X1 plus
think.
X2. What would X1 square be? It would be X1 square plus X2 square plus 2 times X1, X2. But since they are independent, the product expectation of this, or okay, let me not go to this. I will do one thing. I'll just, let me not go here. 1 second. Let me not confuse you people. So is it clear that expectation of X if the Bernoulli binomial is P? Till here, is it clear?
Yes, ma'am. It's clear.
Yes,
The
ma'am.
binomial random variable, it is P into P. I'm just going to add it 10 times. So I get expectation of a binomial random variable is n into p. Okay. Similarly, what would be the variance of x? Variance of x, again, these come from properties of variance. Expectation of x plus y for any two random variables is expectation of x plus expectation of y. Okay. Variance, the variance of x plus y would be variance of x plus variance of y if x and y are independent of each other. And I can extend it to multiple cases. So what would be variance of x1 plus x2 plus x3? If x1, x2 are independent, it would be variance of x1 plus variance of x2 plus variance of x3. Okay. Now I am interested in knowing what is variance of x, which will be variance of x1 plus x2 plus xn. But since x1, x2, xn are independent, this is going to be variance of x1 plus variance of x2 up to variance of xn. Till here, is it clear?
Yes, ma'am.
Yes, ma'am.
But what is
Yes,
the
ma'am.
variance of x1? Variance of x1. x1 is a Bernoulli. So this is p into 1 plus p. This is p into 1 minus p, sorry. And this is p into 1 minus p. So I'm adding p into 1 minus p n times. So the variance is going to be n into p into 1 minus p. So if I have x is a binomial random variable with parameter n and p, the expectation of that random variable is n into p. The variance of that random variable is n into p into 1 minus p. Is this clear?
Yes, ma'am.
Any questions?
Yes, ma'am.
Right? So what was the key thing here? This D was the key. Okay. Now suppose I do not have this independent notion. Okay. So this limitation, suppose I don't have this independent notion. Here you can see head, tail are independent. Whereas here I start with 4 white and 3 blue balls. Okay. This is my first trial. What is the chance of picking up a blue ball? It is going to be, or white and black ball. Black ball is 3 by 7. White ball is 4 by 7. Yeah. Agreed. Now what I'm doing is, if I find a black ball, I'm going to, now how many balls are remaining here?
6 ball.
I'm not replacing. So 6 balls. It is 4 white and 2 black. Here it would be, if it's a white ball, 3 white and 3 black. Agreed? I'm not
Yes,
replacing it.
Yes,
Now,
ma'am.
what is the chance of a black ball here? It is going to be 2 by 6, which is not the same as 3 by 7. White ball is going to be 4 by 6. Again, here a white ball is going to be 3 by 6. A black ball is going to be 3 by 6. So you can see that you have what we call as not independent and not identical. Is that clear?
Yes, ma'am.
Right?
Yes,
So
ma'am.
where we introduce what is called the hypergeometric distribution. Okay. For the hypergeometric distribution, we divide the entire population into 2 independent subsets. So in this case, it was a black ball and a white ball. Okay. And then it has changing probabilities, that is not independent, and the probability of success is not the same. Okay. So this, for a hypergeometric distribution, I have a fixed number of trials, but the probability of success is not the same from trial to trial. So that is the difference between a hypergeometric and a binomial. In a binomial, the probability of success was the same from trial to trial. Agreed? Whereas here, the probability of success is not the same from trial to trial. Is this clear? The difference between the hypergeometric assumption and the binomial assumption characterization?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Yes, again, you're talking about the number of successes. So to understand the hypergeometric, I suppose that I have n items, capital N items, of which I had m of a particular type, say black. Then how many would be of white? It would be capital N minus m. Suppose n equal to 50, of which I had 20 which were black. Then how many white would I have?
30.
30, right? I am sampling 10 items, small n equal to 10. Okay, I'm sampling small n equal to 10. Again, when I'm sampling 10 items out of this, then I could have a mixture of black and white in that. Would you agree?
Yes, ma'am.
Right. So now what are the possible values? And I'm counting the number of black balls in this sample of 10 items. What are the possible values I can have?
0 to 10.
0 to 10. I could have no black balls, or I could have one black ball, or I could have two black balls. Is that clear? Right?
Yes,
Yes,
ma'am.
ma'am.
Yes,
The
ma'am.
sample should
Right.
be mixed of both black and white, right, madam?
It could be, it need not be. If X is taking the value 0, I'm having all the 10 white balls, right?
Okay. No, I'm thinking like as a sample, we should be mixing black and
No,
white,
I'm
right?
just picking up
It should-
balls from there. It could be. That's why X is X. The 0 is a perfectly valid value. What is the chance that X equal to 0? I'm taking only white balls. And my sample
Okay.
has only white balls, no black balls.
Got it.
Got it? Yeah. So what is the chance of X equal to X? So here a small condition is, suppose I was taking the 40. Okay, then X could not have, 40 is the thing. Then necessarily I need to have a black ball also. Would you see that? If my sample size was n. So it depends on what is your sample size also. But for now, I'm just restricting myself to the case that n is 10. Is that clear? If I
Yes,
had
ma'am.
taken 40,
Yep,
right?
yep.
I needed black balls. Definitely I need black balls because I have only 30 white balls. I cannot have a sample of entirely white balls. Do you see that?
Yep.
Yes, ma'am.
Yeah.
Yes,
So
ma'am.
the way this is just I've chosen 10. So my values are of this small x is between 0 and n. Is that clear? Now, what is the way I can pick up 10 balls from 50 balls? How many ways can I pick up 10 balls from 50 balls? The total number of samples.
10C50.
10 ways.
50C10, right?
Sorry, 50C10.
50C10. So in general, it is going to be n choose n. This is the total number of ways I can pick up small sample n from capital N. Agreed?
Yes, ma'am.
How many ways can I pick up x balls from m balls? That would be m choose x.
Yes.
And this is the n minus m choose n minus x is the number of ways of picking n minus x from n minus m.
Yes, ma'am.
So the probability of n equal to x is going to be this numerator by the total number of ways of picking up small n from capital N. And x takes the value 0 to n. This is what we call a hypergeometric distribution. Is this clear?
Yes,
Yes,
ma'am. It's
ma'am.
clear, ma'am.
Yeah. So the expectation. So now if you go back here, okay, in this example, I had this ball. So what is the value of here? What is the value I was looking at here is, this is x equal to 2 because black and black, right? Here, black and white, white and black. I'm counting the number of black balls in both the two trials, right? What are the number of black balls in these two trials? It is 2, right? B1, B2. Here it is 1. Black W or W1, it is x equal to 1. Here, no black balls, so x equal to 0. Is this clear? That I'm counting the again number of black balls only. Is that clear?
Yes,
Yes,
ma'am. It's
ma'am.
clear.
Right. So now you can see that x
Ma'am,
again
can you
takes.
explain this thing
Yeah.
again?
Let's go back here. See, earlier, if I had, let me contrast it with your head tail, right? I had, suppose I'm looking at having a head and a tail, or a black ball and a white ball. Okay. Imagine I had 4 black balls and 3 black balls and 4 white balls. First thing is sampling with replacement. I'm picking up one ball. What are the possible outcomes? It could be either a black or a white. Agreed?
Yes, ma'am.
What is the chance with which I pick up a black? It's going to be 3 by 7. Pick up a white, it's going to be 4 by 7.
4
Is this
by
also
7.
clear? I
Yes,
replace the balls. Now in the second thing, how many balls are available? Again 3 black
Same.
and 4 white. So
Yes,
what is the chance with which I pick up the second ball? It's again going to be
3
3 by
by
7.
7 and
This
4
is
by
going to be
7.
4 by 7.
This
Okay.
ID,
This is
IID.
again going to be B and W. This is again going to be 3 by 7 and 4 by 7. So far, so good. Now
Yes,
I'm
ma'am.
counting the number of black balls in 2 trials. So I could either be a BB or I could be a BW, WB or a WW. Is it clear? This corresponds to X equal to 2. This corresponds to X equal to 1 and this corresponds to X equal to 0. Till here, is it clear?
Yes.
Now, when I had identical with replacement, it was identical, right? And independent. Whereas here it is not identical and independent. Is this clear? The difference?
Yes, because
So
yes,
now
ma'am.
again, in both the cases, X was taking the value 0, 1, 2, but the probabilities with which it's happening, in this case, it's a hypergeometric. In this case, it's a binomial. Till here, is it clear?
Yes, ma'am.
Right. So now that is what is the difference between a binomial and a hypergeometric distribution. Is this clear? So now you can
Yes.
see that I have capital N equal to 7. Okay, I have 7 with M equal to 3. So black is 3, black, black, black. How many whites would I have? 4, right? I'm choosing samples of size 2. Okay, what are the possible? Again, in this, what could happen? In this size samples of size 2, what are the values I could take? I could get a black and a
Two
black.
black.
Can I get a black and a black?
Yes.
Can I get a black and a white?
Yes, ma'am.
Yes, ma'am.
Can I get both
Wha-
whites?
Yes.
Yes, ma'am.
This corresponds to, so what are the values this X is taking? I'm counting the number of black balls in that sample. So what are the values X can take?
0, 1,
2.
2, ma'am.
0, 1,
0, 1,
and
and
2.
2. Yes.
Right? And this is the probability with which it takes the value 0, 1, 2. This is M choose I. N minus M is N minus M. Choose M minus I. Okay, N minus I. N choose N. That's what I have written here. Is this clear?
Yes, ma'am.
Yes, ma'am.
Right? That is how I got the probability mass function of a hypergeometric. The thing that you need to understand is here it is the probability, even though it looks very similar to a binomial, but it does not have the same probability. Is that clear?
Yes, ma'am.
Okay.
Yes, ma'am.
So what is the expectation? I'm not going to, in the interest of time, I'm not going to go back to this, but the expectation, again, I have capital N, small n, and M. I'm specifying the distribution with these parameters, right? I can write it as N into M by N. This also, you can see that I can write it as N into M by N. Would you look at, see, is it clear?
Yes, ma'am. It's clear.
Right? Now the variance is also N into M by N. Okay. And you look at this, I can write it as N into 1 minus M by N. Can I do that? N by N into 1 minus M by N. I can write this. See, 1 second. I can write this as N into M by N. I can write this as N into 1 minus, I'm just taking N common, N by N. So I can write this as N by N minus M by N. Would you all agree with me? Which is 1 minus, I can write this as N by N minus M by N. Can I?
Yes,
I can't.
ma'am.
Yes, ma'am.
Right. Right. I can do this, right? Which is 1
Yes,
minus M
ma'am.
by N. So this, I can write this variance as N into M by N into 1 minus M by N. Okay. And now let's look at this term. This term I can write as N into 1 minus N by N divided by N into 1 minus 1 by N. Can I write it that way? Which will be 1 minus, which is nothing but 1 minus N by N into 1 minus N, 1 by N.
Yes.
Right?
Yes, ma'am.
Now, if this N is large, okay, these two terms would be, this would be infinity, this would be infinity, this would go to 0. Would you all agree if capital N is large?
Yes, ma'am. 1 by N.
Right?
It will be.
So this term would become only 1.
Yes.
Now this M by N, right? For sufficiently this one, you can see that this resembles something. Suppose this m by n, I replace it by some p star or p hat. This would be n into p hat into n p hat into 1 minus p hat, right? So you can see that for some values of this n sufficiently large, this already you've seen. Have you seen some value where expectation of x was np hat and variance was np hat into 1 minus p hat? Have you seen these expressions before?
Yes, ma'am.
Where?
Binomial.
For binomial, right?
Binomial.
So that's what you can see, that as my n increases, okay, as my n increases, what you see is the blue is binomial, the red is hypergeometric. Okay, as n increases, you can see that the binomial distribution and the hypergeometric distribution are the same. Can you see that? Almost the same, right? As
Yes,
n
ma'am.
increases,
Yes, ma'am.
right? That is something which I wanted to show. So far so good. Is this clear?
Yes.
Yes.
Yeah.
Now the next important distribution is what we refer to as a Poisson distribution. In the Poisson distribution, again, it's a discrete distribution. Now, what you do in a Poisson distribution is you count the number of events that happen either in an interval of time or in an interval of space. For example, if you are interested in knowing what is the number of vehicles passing through a traffic intersection in an interval of time between 9 and 10 a.m. or the number of defects in a interval of space, that is, I have a manufactured cardboard and I'm looking at the number of defects. This is interval of space. Again, what am I counting? I'm counting something, namely number of defects or number of vehicles, number of accidents. Again, we are counting the number. Is that clear? So in situations like this, we model it as a Poisson random variable. So far, so good. So if X is going to denote the number of times that event occurs, this event could be the number of accidents, it could be number of vehicles, it could be number of mistakes, it could be number of defects. Okay. Then I say that X follows a Poisson distribution with parameter lambda, where this lambda is the average, or events happen with an average rate at which the events happen. Is this clear?
Yes, yes.
When you want to model events, or you're counting the number of events that happen in a fixed interval of time, which could be number of vehicles, number of accidents, number of people, where you're counting the number of events happening in a fixed interval of time, or as I said, number of defects, number of mistakes in a fixed interval of space, then you model it as a Poisson distribution. Okay. Or number of people entering a mall in a fixed interval of time. What would you model it as? Number of people entering a mall in a fixed interval of time. You'd model it as a Poisson distribution. Okay. So given the average number of lambda events per interval, the PMF of the Poisson distribution is given as e to the power of minus lambda, lambda to the power of x by x factorial. Notice that x takes the value 0, 1, 2. This is countably infinite. So far, we have had values that were finite. Is this clear? Yeah?
Yes.
Yes,
Yeah, please. There was a doubt?
Ma'am, could you just explain about that space factor?
See, space is nothing but, suppose I have a cardboard, okay, long, some 100 meters by 100 meters, right? And I'm looking at number of defects in this cardboard. I've cut this card, or imagine that I have a piece of leather, okay, but that is, I want to make shoes out of that leather. The leather has defects. I want to count how many defects I have in this piece of leather. So that is in space, right? What I mean by space is, it is in a dimensional space. So I could either talk about it in time. For example, if I'm talking about, see, suppose my leather is cut in this cafe. This could be a defect here. 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 I'm counting the number of defects in the space. Is that clear? By space, I mean, this is the space. Is that clear?
Yes, ma'am.
Right?
Yeah.
Yes.
in a paper, or you think that this is a sheet of paper, I'm counting at the number of defects. Or if I have written something, I'm counting at the number of spelling mistakes in this paragraph. That's also a space. Is it clear?
Okay. Yes,
Right?
ma'am.
So that's why you see the number of spelling mistakes or number of misprints in a book. All of them will follow a Poisson distribution, because a book is again a space, right? It's not time. I can think of number of misprints in a book, a number of spelling mistakes in a book. All of them will follow a Poisson distribution. Is that clear?
Yes,
Yes,
ma'am.
ma'am.
It's clear.
Yes,
Then
ma'am.
that distribution, the probability mass function, is given by e to the power of minus lambda, lambda to the power of x by x factorial. See, x here takes, because I do not know how many mistakes could be there. So the value that x takes goes from 0 to infinity. Is that clear? So this is very important. Whenever you're talking about a random variable, you need to know what are the possible values that random variable would take. That is very, very important. Okay. So the possible values the random variable is going to take is 0 to infinity. Any questions so far?
No,
So
ma'am.
this again, this
This
has an
lambda,
lambda
this
is just it's a parameter. It's the average rate at which that happens. Okay. Right. For example, I'm talking a number of telephone, this one or anything, that lambda will give me that rate. So the expectation of the Poisson random variable and the variance, both of them are equal to lambda. And if you go back to the lectures, we have actually derived this to show that both the expected value and the variance is equal to lambda. Okay. Any questions so far?
Ma'am, it's only lambda or 1 by lambda?
No, it would be lambda, right? Expectation and lambda is the average rate. So the expectation and the variance would be equal to lambda, the same parameter. You're getting confused with exponential. This is not exponential.
Okay, ma'am.
Okay. So now we move on to the last module. So what we have done here is, so I started by, okay, so we reviewed what was a random variable, probability mass function, cumulative distribution function. Then we introduced the binomial, the hypergeometric, then the Poisson distribution. Okay, this is what we did. Now we move on to the last module, which is on continuous distributions. Any questions till this point? Is it clear? I know
Yes,
we are
it's clear.
ma'am,
we are
this
pushing in 4 weeks here, but this is an overview and a revision. Yeah, there was a question, please.
no, this Poisson distribution,
Yeah.
is it generalized or is it specific for a example or a distribution,
No,
ma'am?
any time, see, whenever you're counting, for example, if you're looking at number of vehicles passing through a traffic intersection, number of accidents happening at a traffic intersection in a fixed interval of time, number of people withdrawing money in a fixed interval of time of 15 minutes, or number of telephone calls at a call center, all these are examples. Number of typos in a book, number of defects in a wire cable of finite length, number of defects per meter in a roll of cloth, in a roll of
No,
whatever
so
you.
this lambda plays a crucial role, like it seems.
That is the
So this,
average rate, right? You're talking about an average number of lambda events. What is this event? This could be defects. It could be the number of calls. The event here in the first example is number of vehicles. An event arriving is an event. Okay, number of people is an event. Number of telephone calls. So that is how this lambda is nothing but the average number of lambda events, or an arrival rate, as you call it. Is that clear?
okay, is this lambda for the whole? It is for infinite interval, or is it for specific
No, it is
interval?
no, it would not be. See, lambda is what you would be given to you. Is it
Okay.
clear?
Yes, ma'am.
Based on
It,
what is this lambda, you can find out what it would be. That was how your examples would have taught you. Okay.
okay. Well, I just had a doubt that this
Yeah.
lambda is calculated for for infinite time, or is it for specific
No, see,
interval
for
for which
example,
again?
if I, no, not for infinite time or anything. You know that something is going to happen with a certain lambda, right?
Okay.
Is
Yes.
that clear?
Okay.
Okay.
Yes.
That
Yes.
is what I'm trying to capture here. Let me try and
It
pull
is
out an
something like the expectation, ma'am.
expectation is lambda. Actually, expectation is lambda in this case.
Okay. That's what I wanted to know.
Yeah,
that
expectation is lambda in this case. It's not something like expectation. It is expectation.
It's yes. Got
Okay.
it. Yes.
For example, see, suppose I'm looking at the number of vehicles which are, or let me look at this. Suppose I tell you that number of vehicles that are passing through a particular thing is, this is an example. 1 second, let me pull out an example so that I can explain that. Yeah, number of accidents in a factory per week, okay, is happening with an average of 0.5. Is the question clear?
Yes, ma'am.
Now, what is it modeled in interval of space or interval of time here? Number of accidents happening per week in a factory, okay, is happening with an average of 0.5.
Time, ma'am.
It is average time. What is the average here? So what are your parameters
0.5.
here? This lambda is 0.5.
0.5.
Is that clear?
Yes.
So it's not
Yes.
anything. So that is how you're finding it. Is that clear?
Yes. Yes.
Right. Okay, that's how you find it out. Suppose the number of defects again. Right.
Ma'am, you said
Again,
that number of accidents per week, ma'am.
the
The
so
lambda,
that lambda
is,
equal to 0.5 because
yes,
that is the
ma'am.
average.
Then,
Lambda equal to 0.5. Yeah.
Then this random variable x is also per week.
Yeah, that is how we are defining it, right?
So even the x will be per week only. Number of accidents per week is also is x.
Yeah, per that interval, whatever interval of time you're defining.
Okay.
Yeah.
Yes.
Suppose it is per minute or per week, it would be the same thing. What is the
Same
time
thing.
interval you're defining?
Yes. Yes.
The fixed
Got it.
interval of time or fixed interval of space. Suppose I'm looking at the number of defects in a paper, in a roll of cloth. Okay. I'm saying is about 0.5 defects per meter.
Yes.
What is your lambda there?
0.5 defects
Per meter. So your x is going to be the number of defects per meter.
Yes.
What would be your lambda?
Lambda is 0.5 per meter. So x also will be measured in the same scale.
So I want to know what is the probability that there are exactly 3 defects. It would be e to the power of minus 0.5, 0.5 to the power of 3 by 3 factorial.
But this 3 defects per meter, no, ma'am?
Yeah, x is going to be 3 defects per meter. Yeah, because everything is in the same interval of time or space.
Yes. Yes.
Is it clear?
Yes, ma'am. It's clear.
Right.
Thank you, ma'am.
Okay.
Yes,
see, but again, you need to be very careful. So if you look at that 500 mistakes and 500 pages and everything, what is the number of mistakes per page?
Per page. Okay.
You'll take it that way, right?
Yeah, we have to accommodate
Depends on what is
according
the
to
question asked. Then you'll have to
Yes.
find out what is your, is that clear?
Yes,
if I
ma'am.
have
Yes, ma'am. Got it, ma'am.
1500 mistakes and 500 pages,
500
what is the
pages.
mistakes per page?
300.
300
Not
or
3, ma'am.
3, right? That
Yes,
is
3,
so.
ma'am.
If I'm asking you if x is the number of mistakes per page,
Per
what
page.
is the, so that lambda would be accordingly
Changing.
you'll define it. Is that clear?
Yes. Yes, ma'am.
Right?
Got it. Yes.
Got it?
Yes, ma'am. Thank you, ma'am.
Right. So the next thing that we are going to look at is what is referred to as a uniform distribution. Just to say, define what was a discrete uniform distribution to be a random variable which took different values with the same probability. Now we are moving on to the space of continuous distribution. So one of the things that we need to understand when we are defining continuous distribution is, now when I talked about discrete distributions, okay, when I talked about discrete distribution, can you see my one note?
Yes, ma'am.
Yeah, when I talked about discrete distribution, I said x takes these values which I called x1, x2, x3. I gave x to be a discrete values. I knew what were the values, right? Now, whereas suppose I'm looking at a continuous distribution, I'm looking at X taking values in an interval rather than it's taking discrete value. So it can take any value in the interval. Is this distinction clear between discrete and continuous? This is discrete, this is continuous. Is this clear? Here X was taking value X1, X2, X3, X4, X5. Here X can take any value. So I write it as X takes values X1, X2, X3, X4, X5. Here I would write it as X belongs to this interval A to B. Is this clear?
Yes, ma'am, it is clear.
Yes,
So
ma'am.
now here I was defining probability X equal to Xi. Now I'm asking what is the probability X belongs to a particular interval. You see the difference?
Yes, ma'am.
Yes, ma'am.
Okay. So now when I ask, so here we define a random variable X equal or belongs to a random variable. So the equivalent of this probability X equal to Xi, which was a discrete thing, is now going to be a continuous function, which is called a density function. So probability X belongs to any set is this f of X dx. That is how I define a continuous random variable. And this small f is what I call a probability density function. I call this a probability density function.
Can
Now
you
the
repeat,
way
ma'am?
to, yeah.
And the PDF probability density function, please repeat that.
See, for example, suppose I had X taking very close values to each other, right? This way. Is this clear?
Yes.
Right. Okay. Now the probability, what is happening is when I have a, this is becoming, or it's like when you're doing a summation, and summation of very close numbers, summation leads to integration at some point, you would have learned.
Yes, ma'am.
Yes, ma'am.
This is summation, right? So what is happening is, I'm not having X taking these values anymore. I'm having X taking a value on an interval. Is that clear?
Yes, ma'am.
And here it was probability X equal to Xi. Now, instead of that, I'm having a function such that the probability, what is this probability of all these values? It was summation of probability X equal to Xi, right?
Yes, ma'am.
Now, this is going to be, and if you look at it, it would be the area under the curve. If imagine multiple things, this is nothing but this would be the area under the curve. Suppose everything was very close to each other, which
Yes,
I can
ma'am.
write as A to B of some f of X dx. Agreed?
Yes, ma'am. Yes.
And I can write that this is probability X belongs to this A to B is integral A to B f of X dx, the area under the curve. Agreed?
Yes, ma'am.
Yes, ma'am. Yes.
Now, when I talk about a uniform distribution, in the discrete case, I said a distribution where all the probabilities are the same. These are all the same, right? Now, in the continuous case, I have A to B, and if this is f of X, here this was probability X equal to X, right? This is the same. Okay, it is the same. F of X is a constant for all the X which lies between A and B. Okay, it's a constant. I do not know what is this constant, but what should the area under any, what is summation probability X equal to Xi for all Xi? What did we say? If the problem, it is 1. So similarly, if my X takes value only between A and B, what would be the integral A to B f of X dx? It doesn't take value. It will be also equal to 1. Agreed? Now I'm saying this f of X takes a constant value here. So this is A to B, a constant times dx equal to 1. What is this constant? So I have here, so what would this be? This would be constant times b minus a equal to 1. So what is the value of the constant?
1 by b minus a.
1 by b minus a. So this, so a discrete or a continuous distribution has a probability distribution which is 1 by b minus a. A is less than or equal to x is less than or equal to b. So in a continuous distribution, we say that probability x takes a value equal to 0. Why is it 0? Is it cannot take a particular value. It takes always a value in an interval. Is this clear?
Yes, ma'am.
Yes, ma'am.
This thing, can you repeat, ma'am? This thing,
See,
the last
which
p
one?
of x is equal to x.
This one? Till
Yes,
here,
ma'am.
is it clear?
Yeah,
This
this
k
is
is
clear.
b
ma'am.
minus a.
But
So
just
if
the
k is b
statement,
minus a, right? So if k is b minus a, my f of x, I can write the probability density function as 1 by b minus a for all a is less than x is less than b and 0 otherwise. Okay. So when I'm talking about a continuous random variable, I always talk about x belonging to some interval. Okay. AI, BI. Okay. So the chance that x takes a particular value is defined to be 0. It always belongs to an interval. Is it clear? This is x taking a particular value. Is that clear? X cannot take a particular value. X can only belong to an interval because it is a constant. Is that clear? Yes or no?
Yes, ma'am. Yes, ma'am. It's clear.
Right. So now if this is there, again, if you look at the cumulative distribution function, cumulative distribution function is also if x is less than or equal to a. Now again, let's come back here. This is my x. This was my f of x, right? And between any a and b, it was 1 by b minus a, right? This is 1 by b minus a. What is probability x is less than or equal to x, sorry, f of x, right? What can you say about the probability of here? Till here it is 0, right? Even here it is 0. What is probability x is less than or equal to a? Cumulative probability of all the, if I add up all the probability of x is less than or equal to a, it is going to be 0,
yes.
right? At x equal to a, it is 1 by b minus a, right?
Yes.
But what is it at a plus 1?
What is a plus 1?
So f of x,
it's
see, I
also
know
1.
that, see, f of x is equal to 1 by b minus a for all a is less than x is less than b. Is that clear?
Yes.
Right?
Yes.
So what is it at this point? It is 1 by b minus a, right? Agreed?
Yes, ma'am.
Now what would it, so probability, so if I'm looking at probability x is less than or equal to, let me have it as c. Okay, I'm looking at this probability. Would you agree?
Yes, ma'am.
This is the cumulative probability. Now what is this? This is 1 by b minus a. This is c minus a.
Yes, ma'am.
Right? Now if I look at another point, say d, what would that be? What would be probability x is less than or equal to db?
Yes. Yes, it is less than.
X is less than or equal to c is going to be this thing, right?
Yes, ma'am.
Which would be c minus a by b minus a,
C
right?
minus a by b minus a.
Right? What would it be for d? X is less than or equal to d.
b minus a by b minus a.
B minus a by b minus a.
E?
E minus a by b minus a.
So for now, what would probability x be less than or equal to x be for any x between a and b?
Then it will be x minus a by b minus
a. Till here,
yes.
Is it clear? Now,
yes,
would you all
yes.
agree that I can write this as 1 by b minus a by b minus a plus x by b minus a?
Yes, ma'am. We can write.
Now, this is the equation of a line.
Yes, ma'am.
Mx plus c.
Yes, mx plus c.
Right. So, would you all agree? And what will be x at b? At b, what is the area?
It's x minus b by b.
What is this complete area? What is this area?
A minus
area
b by b minus.
It is b minus a by b minus a. What is that? It would be 1, right?
It will be 1. It will be 1.
Right. So would you all agree that the cumulative distribution function can be given by this? For x is less than a, it is going to be 0. For any x between a and b, it's going to be x minus a and b minus a. And for x greater or equal to b, it's going to be 1. All of you agree this will be the cumulative distribution function?
X
Yes.
greater than equals
Yes,
to
ma'am.
b.
Pardon?
I
It
mean,
would be 1 only, right?
yes,
Because
it will be 1.
beyond this, till it was a to b, okay, we found it, right? Till here it was 0. Then it kept increasing. Then it would remain 1.
Okay.
Because after it is b, everything is 0. It would be whatever it is at b. Whatever is the area up to b only, right?
Yes, ma'am. Yes.
Right. So this is the shape of the cumulative function, and this is a straight line. So we do not have the discontinuities that we had in a discrete case. You can see that this x minus a by b minus a is nothing but minus a by b minus a plus 1 by b minus a into x, which is the equation of a straight line. Would you all agree?
Yes, ma'am.
Right? So the cumulative distribution function of a uniform distribution is given by this way. Now, how do I compute the expectation of a random variable? So what is an expectation? Suppose I have f of x is my, suppose f of x is my PDF, okay? Then expectation of the x is given as x into f of x. This is similar as x into probability x equal to x over all x, or xi into probability x equal to x over all xi. Over the range I have defined, it would be integral x into f of x. Is that clear?
Yes, ma'am.
Right? So now let's look. And similarly, variance of x is going to be expectation of x square minus expectation of x whole square. This is already. What would be expectation of x square? This would be x square into f of x over the range we have defined. Is this clear?
Yes, ma'am.
Now let's apply this to the uniform distribution. What did we have? We had x is a uniform between a to b. Okay. And what was my f of x? My f of x was 1 by b minus a. For all a is less than x is less than b, 0 otherwise. What would be my expectation of x? This is going to be a to b because I've only defined it in a to b. This is the range I have defined it for. Yes, x into 1 by b minus a. So what would this be? I can remove this 1 by b minus a outside. A to b x. Now what is this definite integral?
X square by 2.
X square by 2.
Okay, so 1 by b minus a. X square by 2 would be b square minus a square by 2.
Yes.
What would this be? This is b minus a plus b plus a. So I'll get this as b plus a by 2.
B plus a.
Right? Is that clear?
Yes, ma'am. It's clear. It's for uniform.
Yeah, for uniform distribution. Continuous uniform distribution. Okay. The expectation is b plus a by 2. And the variance you can check is, I think it is b square minus a square by 2. Just check. There could be some typo here. Okay. Please check it. But you know how to get it, right? I got what is expectation. This is b square plus ab. I'll get a b square minus a square. I think
It was
this
a typing mistake.
It's just a typing mistake.
Yes,
okay.
Yes.
Is that clear?
Yes, ma'am. It's clear.
Right. Now the next distribution is what is called, I'm going to skip the triangular distribution. I'm going to go to the exponential distribution. The exponential distribution, we say a continuous random variable has a probability distribution. Now, see, don't get confused with this lambda and the Poisson lambda. I could just use this on some alpha. Okay. It is just a thing, right? Parameter. It could be anything. I could call it alpha also. This has nothing to do with the lambda of exponential. Is that clear?
Okay,
I could just call it some alpha also. No problem. It's just a parameter, but it is greater than 0. If for any alpha greater than 0, f of x is alpha e to the power of minus alpha x, 0 otherwise. Then it is called an exponential distribution. The exponential distribution is very popular when you are trying to model basically inter-arrival times or service times and things like that. You assume that the distribution is a exponential distribution. Is that clear, please? Now, what would be the CDF? this CDF is going to be probability x is less than or equal to x, which is going to be what? 0 to x, because x is taking only values greater or equal to 0. F of x, what is f of x? E to the power of minus alpha x dx. What would this be? Alpha into what is the integral of e to the power of minus alpha x dx?
E to the power minus alpha x by minus alpha.
Minus alpha.
Right, this one. So what would I get? So you can see that this minus alpha would cancel out, right? So I would get f of x is equal to 1 minus e to the power of minus alpha x. Is that clear?
Yes.
1 minus.
Right, this is the distribution function. Is that clear? Cumulative distribution function. Agreed?
Ma'am, excuse me, ma'am. Could
Yeah.
you please explain what is that exponential distribution? Generally, not about the formula. What
See,
is the
exponential distribution, typically the x in a continuous distribution measures, right? Agreed?
Yes, ma'am. Yes,
Now,
ma'am.
suppose I'm having 10 people, I'm computing what is the time. I have a queue that is being built up. What are the two possible times? There's a time between arrivals of two people into the queue. Suppose they are getting served. There is a service time also. Is this time deterministic or is it random?
If it is, whenever the time arises, it is an exponential like that, or maybe in some other cases
One
also
of the
there.
one of the main things is it could be, for example, I'll show you what we considered in this one for an example. Okay, if you look at it, arises as the distribution of amount of time until some specific event occurs, and this event could be the inter-arrival times. Is that clear? Okay, or it could be the service time. I'm measuring the length of a phone call. See here, I'm measuring. What am I measuring? What is the event or what is the quantity of interest for me here?
Length of your phone call.
Phone call. Okay.
Yeah.
And will the length of the phone call be fixed or will it be random?
It will be random.
It would be random. So I'm assuming that this length of the phone call is a random variable, and one of the ways I'm modeling it is as an exponential random variable. So what is the parameter here? I'm assuming that this parameter is lambda equal to 0.1. So what does this say is, you can see the distribution for different lambdas, what is happening to the graph of this distribution, and what is the this one PDF, right? Can you see that? Right?
Yes, ma'am.
So
Yes.
based on this, I can answer, if I know that my assumption is an exponential distribution, I want to know what is the probability that, suppose you have entered a queue and you know that the time you wait for the to be served is an exponential random variable with parameter 0.1, and somebody wants to know what is the chance that I'll have to wait for more than 10 minutes. For example, you're going for some passport application, right?
Okay.
And you know that the length of the time you spend, right, is an exponential random variable with parameter lambda equal to 0.1. Or now being the voting season, today I casted my vote. You go to vote and you see that the time spent, okay, the length of time a person spends in that is exponential inter-arrival time or some random variable with parameter lambda 1. What is the chance that you're going to spend for more than 10 minutes in the queue? Is that a valid question to ask? Right? So
yes,
if
yes.
I know that this is the distribution, I can find out this is nothing but probability x is greater than 10 is 1 minus probability x is less than or equal to 10. I know that cumulative distribution function is 1 minus e to the power minus lambda a. Okay, my lambda is 0.1. I can find it as minus 0.1, which is 0.368. Is that clear?
Yes, ma'am.
And probability 10 is less than x is less than 20 is f of 20 minus f of 10. I just plug in the values and I know that there's a 23% chance that you'll wait between 10 minutes and 20 minutes. And there's a greater chance because probability x is greater than 10 is going to be greater than this probability. It is going to be 0.368. Is that clear? That is where you apply the notion of an exponential distribution. Is
Okay,
this
ma'am.
clear?
Okay, ma'am. Okay, ma'am. Thank you.
Right. Okay.
Yes.
Now the last distribution is what we call a normal distribution. The norm, yeah.
Ma'am, you told cumulative distribution that the variance and expectation, which was a typo mistake. Can you tell like what's the variance and the expectation?
For the uniform.
Yes. Cumulative
Yeah.
distribution, yes, ma'am.
Cumulative,
No,
I
no.
didn't
She
say.
is
I said there is a
talking about
typo
uniform.
here. I said
Yes.
there's a typo here. You please do it. I just have 10 minutes to finish it. Okay. Right.
Okay,
I think
ma'am.
these things you can verify it very quickly. I don't have to tell it here. Okay. I'll just go through the last distribution, which is called the normal distribution. The normal distribution has two parameters. So far, we have seen distributions with a single parameter, right? Or hypergeometric had more than one parameter. Binomial had parameters which were n and p. Okay, whereas exponential had only lambda, Poisson had only lambda as their parameters. Okay, now a normal distribution is determined by two parameters and they are known as the mean and the variance. And the density function, you have to know what is the density function. That density function is given to you again, right? Which is x. This is the density function. Now, the shape of a normal distribution is symmetric about the mean. This is why all of them refer to as a bell-shaped curve. The normal distribution, the key things that you need to understand is it is symmetric around the mean. And the height of this curve is when x equal to mu, that is the highest. So that is where the height is 0.399. And this is what we are going to say, that you always need to understand that the area under the curve will always remain 1, because for any continuous distribution over the range, and for a normal it is between minus infinity to infinity, the area under the curve is always going to be equal to 1, any continuous distribution. So if I ask you to plot same mu and different sigma, you know that this sigma is the least, this is medium, and this is this one. It is incorrect to plot same mu and different sigma. I have seen many people who plotted this way. It is incorrect to plot it this way. This is wrong. This is correct. Okay. Similarly, same mu, same sigma and different mu, the graphs have the same distribution, but they are shifted. These are all just basic things that you need to remember. Now, what do I mean by symmetric around the mean? What it implies is this area blue is the same as the area green, which is equal to half, and that is given as probability x is less than or equal to mu is same as probability x is greater or equal to mu, which is equal to half. This is what we mean by symmetric around the mean. For any general mu, the idea and the most important thing that you need to understand from a normal distribution is what we call the approximation rule. What the approximation rule says is, suppose I have a random variable x, which is distributed with a mean mu and standard deviation sigma. Suppose this is the marks of 100 students in a class, okay, which has a particular mean, say mean is 75 and standard deviation 5. Okay, suppose I have 100 students in a class and I say mean is 75, standard deviation is 5. What is mu plus sigma? What is mu plus sigma?
80.
80. What is mu plus 2 sigma?
85.
85.
Mu plus 3 sigma?
90.
90. Mu minus sigma?
75. 70.
70, right? Mu minus 2 sigma?
65.
65.
Mu minus 3 sigma? 60.
60.
Is this clear? Right? So what the approximation rule says is, suppose there are 100 students in the class and the average mark is 75 and I'm saying the standard deviation is 5. 68 of them would have got between 70 and 80. That's what it means, because this is 75, this is 70, this is 80. 68 of them. How many would have got between 65 and 85? This is 65 and 85. 95% would be between 65 and 95. How many would be between 60 and 90? 99.7. Okay, there is a small percentage which would be here. Is that clear? Okay.
Yes, ma'am.
Yes,
Okay.
ma'am.
Now, given this, what is the percentage who would have got between 80 and 85? Or how many percentage would have got above 75? 75 is the mean, median, and mode. What is the percentage you would have got above 75?
0.5.
0.5.
Half, ma'am.
Right? Half.
Half.
0.5. 50% have got above 75. Right?
Yes.
And that is why, because the median and the mean are the same in a normal distribution. If I specify the mean, I can also say that 50% have got above 75. And this notion of this approximation rule and application of the approximation rule is very, very important. Okay. So we have discussed what is the application of the approximation rule. That becomes very important. And in the interest of time, I think these are very similar. What else do you need to know? Find a mu given a probability and sigma, and find sigma given a probability and mu. And how do you compare two distributions? This is again, you can see that here I have given the expectation for one is 100, the other is 105. And you can just see that depending on this, which has a greater area. You should have a knack to draw these pictures. Okay. Now, one of the most important things that people used is what is called a standard normal distribution. A standard normal distribution is a normal distribution where the mean is 0 and standard deviation equal to 1. And it is typically referred to as Z. So Z is a normal distribution with mean equal to 0 and standard deviation equal to 1. The same approximation rule can be applied to a standard normal distribution also. And this is also important, that once you know what is a standard normal distribution, how do you compute the values in terms of Z? For example, what is the probability that Z would lie between -1 and +1?
It is
0.68.
0.68.
0.68.
0.68. -2 and 2, it is 0.95, right? What is it between -2 and -1?
-2 and -1, it's point.
You need to, what, okay, -1 and 0. Forget about -2 and -1. -1 and 0.
0.34.
0.34. Okay. You know that. And -2 and 0?
-2 and 0. It
would be
91. 60.
-2 and plus 0 is 0.95 by 2,
47.
right?
Yes.
47.5.
-2. So you know what is -2 and 0, -1 and 0. So -2 and 1 would be the difference. So these are the computations that you should be able to solve. Okay. And of course, standard normal tables, how you look at it, that should also be what you should be doing. And I've just included some values here. Now, this is very important. We say that this is a z-score, which is x minus mu by sigma. This is what we refer to as standardization. Because I can convert any normal variable with a mu and sigma to a standard normal variable with mean 0 and sigma by applying this x is z equal to x minus mu by sigma, so that probability x is less than a is same as probability z is less than a minus mu by sigma. You don't have to remember the standard normal table. Please, no. Nobody would expect you to remember the standard normal table. It would be at best given to you, or you can find out with whatever. I do not know how Prashant should be able to tell you how the standard normal values would be given to you. Okay. So what we did later is, I'm not going to answer specific questions here. You can see that I've just put all the examples here. Okay. There are properties. I think we are just overshooting time. So Prashant, I think I can stop here, right?
Yes, ma'am. Yes, ma'am. We can stop and rest the
Yeah.
remaining thing
Yeah.
we will discuss in
Yeah, I think
our session.
it's already 8 o'clock and I would like to stop here. If there
Sure.
are any questions on what I have discussed so far, I'll share these slides also, but most of them are already what you have done, but I think I'll just share this with Prashant. He will share it with you so that you have a concise revision. Except for the normal distribution, I think everything else I have done it very much. Kiran, if there are any specific questions, please address that to Prashant and his team. He will answer it. Okay?
Ma'am, I have a question.
Yeah, please. Yeah.
In these kind of questions, how to interpret what do you mean by number of standard deviations and number of observations?
I didn't get your
How
question,
to interpret?
please.
Like in some questions like this in normal distribution,
Yeah.
how to interpret number of observations or
Number
number
of
of standard
observations is
deviations? Like
not, see, number of
how to
observations will
find?
not give it. For example, I'll give what is x equal to n 15 and 4. You'll be asking what is the probability x is less than 11. Or we'll give you that, okay, x has some mean and given probability. Suppose I know that some x is greater than 16 is 0.975. Tell me what is the expected value. Okay, that is what we'll do. I'm not sure that I understood what you mean by number of observations. These are all probability distributions.
Yeah,
Okay.
but this question was given in activity 12.7.
I'm not going to take any specific activity questions. I think these things can be handled offline by the team. Okay.
Ma'am,
Right. Yeah.
ma'am, I'm having a doubt in continuous uniform distribution in
Yes, let
applying
me
the
go to
formula.
that. Yeah, let me go there and tell me what. Don't give me a question, but tell me. Yeah, what is the
I'm
doubt?
confused with applying the formula, whether I should apply x minus a by b minus a or 1 by b minus a. How can I clarify that?
Okay, let's look at this example that I have given here, right? Okay, you are to meet a friend at 2 p.m. Okay, you are always on time. Your friend will always come at a time uniformly distributed between 0 and time. So this I have written as your friend can come any time between 0 and 60 minutes late. Is that clear? So if your friend, this tells you x is the amount of time you have to wait. X is uniformly distributed 0 to 60. Is that clear?
Yes,
Because he
ma'am.
can come anytime between 2 p.m. and 3 p.m.
Yes, ma'am.
Okay. So if it is x is uniformly distributed between 0 to 60, what is the density function? This is your A and this is your B. Is that clear?
Yes, ma'am.
So your density is 1 by 60. For A is less than x is 0 is less than x is less than 60. Till here, is it clear?
Yes, ma'am.
Now I'm asking, how do I convert this? Probability x is at least 30. That is what this means.
Yes, ma'am.
Now what would I add here? So I am looking at this area. I know this is 1 by 60 now. So I can do as 30 to 60, your 1 by 60 dx. That is what I'm looking at. X is at
Yes, ma'am.
least 30. Is it clear? Probability x is
Yes,
greater or equal to 30 would be x from 30 to 60. Less than 15, it would be 0 to 15, right? Between 10 and 35 would be 10 to 35. Less than 45 would be 0 to 45. All the f of x is going to be the same. Would you agree?
Yes, ma'am.
That's how you're doing. So no, B by NSA is used to find out what is the this one, and probability of x is less than or equal to any A is integral whatever you're looking at. So x is less than or equal to, let me call it C, A to C times f of x dx, and you just apply the integral formula. Is that clear?
Yes, ma'am.
Okay. Yeah, I think I'm going to stop here. If there are any other questions, you can please mark them to Prashant. Okay. I think in the given time, we try to do as much as possible. Yeah. I'll take one more question before I close. Yeah.
Ma'am,
Integration. No, no, no. I cannot explain about integration here. No. Integration is math. I'm not going to talk about math here. Yeah. One more question.
there's a dice whose two sides are marked one side is marked 2 and three sides are marked 3. How
Okay.
do we write the sample space?
You had what are the possible things that outcomes that can come from this dice?
Yes.
What are the possible outcomes? You tell me.
Ma'am, if we throw the
If I roll
dice
the
twice,
die, what are the possible outcomes you'll get?
1, 2, 3.
That's it. You got your sample space.
But if we roll the dice twice, what
How?
is the samples?
Tell me again. If you roll the dice once, you'll get 1. So it will be a 1 1. It will be a 1 2. It will be a 1 3. 2 1 2 2 2 3. The probabilities will not be the same, but this is what you're going to get, right?
Yes.
Okay. And I told you again, I'm not going to take specific questions, but this is how it is, right?
Okay.
Okay. I think I'll stop here. We are just overshot by some time. Okay, then. Prashant, can I close the session?
Yes, ma'am. We can close
Okay.
this. Thank
Right.
you, ma'am.
Thank you
ma'am.
all. Okay. Thank you
Thank
all.
you, ma'am.
Have a
Thank
good
you, ma'am.
weekend.
ma'am.
Thank you all. Have a good weekend. Yeah. Bye.
Thank you. Bye.
Yeah. Thank you.